So I put your next assignment up on the GitHub there yesterday, and here's what it is. Actually, I just have it here in Markdown pad anyway. Okay. So last year I was gifted this beautiful arcade cabinet in my office from Microsoft. These were purchased for a gaming event that they were hosting, a Windows 8 kind of gaming event, and it was basically just sort of purchased for that and then just left in a storage facility in Microsoft, and then they gave it to me. Thankfully, it's sitting in my office, and it's a MAME machine with 35 gigabytes of MAME ROMs on it. You can play any game basically from the last 40 years on it. And it's a really cool arcade cabinet. Has anyone ever played MAME or used MAME in the class? Okay, so I'll show you what MAME is. It's an arcade emulator for old arcade games. And if you play MAME on your PC, it's great. But if you play MAME on this thing, this has a CRT in it. And it has joysticks and buttons and stuff. It's a completely different experience playing a game on this than it is playing on your PC. So that's what it looks like there. That's it playing Pac-Man. And the aim of your assignment, and I've given you lots of inspiration here, is to make a retro graphics style arcade game to run on that arcade cabinet. You can do it in processing. I presume you're all going to do it in processing, okay? You can come up with your own game design for this, right? But I suggest you do what's called a vector graphics style game. And I have some examples of vector graphics games here. You know, just ones. These are games from like the early 80s and the 70s and stuff, right? So this is a game called Lunar Lander. So there's a little character in the middle of the screen. You've got a little procedurally generated landscape. You've got to land in those little flat areas. And there's a little bit of simulated physics in it. So that's an example of the type of game you can make. This obviously is Pong. I'm sure you've all seen Pong and played it. Alright, so Pong is a game that you could make. This is, what's that one called? That's Asteroids, another game you might want to choose to make. This is probably a bit beyond the level of this course. This is Elite. So this is the original Elite. You might know that there's a game called Elite Dangerous, which is coming out very shortly as a big Kickstarter campaign for it. So it's just to show you, this is wireframe vector graphics. Don't even know what that game is. It's an arcade game called Tempest. So that one, GameSpot theme from a few years ago. It's called Battle Zone. It's a 3D vector graphics game from 1980. Again, 3D if you want, but 3D is, do it if you like, but it's not essential for this. Can't remember what the name of that game is, but it's basically a little vector graphics character moving around in a sort of a maze type thing, doing things. Vector graphics games were very popular because at the time that these vector graphics games were being made, the alternative to this was what are called raster graphics games. And raster graphics games were sprites. But the resolution on the displays was quite low. So you look at games from the early 80s and the 70s, they look really, really pixelated. They have this quality which is very popular in games, this retro quality. Lots of people are making retro style games now with 16-bit or 8-bit style pixel graphics. But vector graphics had the advantage in that the lines were always beautifully smooth because they were drawn in a different way than sprites. They were kind of, procedurally drawn or whatever. Anyone know what that's from?
Hitchhiker's Guide to the
That's
Galaxy.
Hitchhiker's Guide to the Galaxy, good man. So, this was actually not generated by a computer. These were hand-drawn to make them look like the vector graphics, which were the sort of, what's the word I'm looking for? Retro future style. This is what the future looked like back in 1980 when I was growing up. The future looked like this. The computers looked like this. They had this vector graphic style. So that's one of the Star Wars games. They're awesome games, these Star Wars games. They're vector graphics games with a little bit of sampled music and sampled speech from the games, from the movies as well. Can't remember what that one is either, but this is the style of art I want you to try and aspire to make for your games. That's another example of Tempest. That's the Star Wars game as well. We can play some of these because I have MAME on this computer here. That's the Star Wars game. That's Tempest again. What's that one? That's Geometry Wars, right? So Geometry Wars is obviously a modern game. There's a new version of Geometry Wars out, but it's inspired by the visual aesthetic, which was popular in the late 70s and the early 90s. This is vector graphics, procedurally drawn style of art. And similarly, this game, does anybody know what this one is? It's one of the greatest games of all time, in my opinion. It's a game called Darwinia, and it's again inspired by art style of the 80s and the 70s. And there's Pac-Man type creatures in this, and the characters that you control are little 2D sprites that move around in a flat shaded 3D world. There's quite a lot of vectors and stuff going on as well. So these are games that were inspired by the vector graphics games. Never mind about that marking scheme. I'll talk to you about the marking scheme and the rubric and stuff now. So that's your challenge. Your challenge is to make a vector graphics style game that will run on that arcade cabinet. My aim is, I think there's 78 people in this class. My aim is to have all 78 of your games running on that arcade cabinet for the State of Play Festival, which takes place on the 7th of February next year. I want them all on the cabinet with a menu at the start which will allow you to choose which game a person can play, and that will be just left there and people will be able to play your games on it. Also, there's the project fair next year. So we've about 200 companies come in for the project fair every year. They're looking for students to recruit and for internships and that. And so your games will all be on the arcade cabinet. Now, I've written yesterday a little framework which I'll go through with you today. And you can use this as your starter code for your games. Now, the only thing it does is it loads up the key bindings for the controls, because the keys on the arcade cabinet, the controls all map to keys on a keyboard. Alright, so when you press the up on the joystick, that maps to the key J, for example. So I'll give you a file with key bindings in it. It's actually a little XML file. So you all know what XML is? What subject would you have done that in? Web dev. Okay, so it's a little XML file. Again, if you're looking for, why do we study games, or why am I so interested in games? Because every game is a little system, and every game has got stuff which is transferable and applicable to lots of other domains in computer science. So we load an XML file with the key bindings. XML is totally the right format for that because it's a hierarchical format. And then I just map it onto two little objects in a scene that you can control using those keys. And that's the starter code which I'll show you. So, yeah, that's my plan, okay? So, in terms of what you have to include, same as the first assignment, a splash screen with instructions, game screen, multiple game screens, and a game over screen. Some constraints on this assignment. You must write all the code yourself, apart from code that you have written as part of this course, or that we wrote as a class. So you can use stuff from my Git repository, or your own code that we wrote in the class. But apart from that, you have to write everything yourself. Okay, so you can't get code off the internet and include it in your assignment. That's disallowed for this assignment. You've got to write it all yourself. Even if you find something on the internet, I expect you to rewrite it and understand it yourself if you're going to include it, okay? It's all about what you can do. The next thing is all the art for your assignment you must make yourself. So you've got two choices to make the art. You can either procedurally draw it. In other words, you can the same sort of art style that I used in the Yask game that we're making, the Space Wars clone game. You can use that art style and you can procedurally draw everything. So you can use hexagons, little simple 2D shapes. Okay? You've got to draw them all. Or if you're like Owen up there and you can draw, you can make your own sprites, but you've got to make them all yourself. So you can't get like Mario sprites on the internet and include them. You've got to make them all yourself. Next thing, the theme for this year's Games Fla. So you guys have been to Games Fla. Isn't it awesome? Yeah. Yes. Do you encourage everybody to go?
Absolutely.
Okay. So the theme for this year's Games Fla is Endless Runners. Guess what? You guys have already made an endless runner. So I'd be quite happy to take a number of your assignments, which were brilliant. Your assignments, first semester assignments, were really, really good. I'd be really happy to submit even some of those for this year's Games Fla. But if you want to do something for this year's Games Fla, the date for that is the 10th of March, right? So you'd need to get your games finished probably maybe by the end of March. But if you want to try and sort of get this towards doing a Games Fla project out of it, you can make an Endless Runner style game as your assignment for this thing over Christmas, and then you can adapt it for Games Fla. And I'll be looking for 5 teams for Games Fla, even though this is an individual assignment, right? So this is something it's like your prep for Games Fla, if you like, rather than your Games Fla submission, right? You can use the mouse as well if you want, because this arcade cabinet has a trackball on it. And do you know what a trackball is? It's just a big ball, and you spin it left and right, and it makes the mouse move on the screen. So you can use that as well if you want to control your game using the mouse, left and right, and then also the joysticks and stuff. Okay. Next thing, you should try and use Git. How many people have got a GitHub account here? Great. How many people have used Git? Maybe done some check-ins and stuff yourself, or just maybe. Okay, so I'll give you a Git tutorial this Friday. So everybody needs to be here this Friday, and I'll video it if you can't come. It will explain to you how to use Git. It's really, really simple. Really simple. And there's only like about 6 or 7 different Git commands you need to remember, and then you'll become a Git master like me. And you love Git, right? Git is like using using an IDE or using processing versus using, we'll say, Notepad to write your code. You know, it's brilliant. Once you start using it, it just transforms how you write software. And also, it's essential. It's a very standard question in a internship interview. You know, what version control system are you familiar with? And then you say Git, and then that just answers that question. And they'll say, show us your Git repository, and you show all your code that you've written up on the Git repository. So you've got to use Git. If you want, I expect you to spend about 2 full days on the assignment. So you have between now and the first week we're back after January. So I don't think that's kind of unreasonable. And I want everybody to do an excellent assignment. I don't want you to submit anything that you're not completely and totally proud of, that you don't think is absolutely the best you can possibly be and your best possible work. Alright, so I'm setting a standard here, and I want you all to step up and do your best work for this assignment, right? I mean, I often think, you know, sometimes, you know, why are we all here in this classroom? We're all here because we're computer scientists. And this is what we do. We write computer programs. That's what you signed up for when you joined this course in first year, right? So, you know, you want to be the best computer scientist and the best programmer you possibly can be. Next of all, yeah, oh, sorry, there's one alternative, but I'm not quite sure if I've worked this out yet. You can also do an Imagine Cut project. If you're not totally sold on the idea of making a game, you can do an Imagine Cut project, but I have to get Stephen Howell from Microsoft in before the end of the semester, and he's a very hard guy to get. So maybe next week I'll get Stephen in to talk about what the Imagine Cut is all about, and you can form a team. But the rubric and marking scheme still applies. So 30% for code, 30% for gameplay, 20% for project management, which will be basically how many Git check-ins there are over the course of your project. So if I see that you make your Git repository at the start, and I see that there's little check-ins, you know, every now and again you're checking in code, that means that you're working on your project over a longer period of time. If I just see one big dump of a project right at the end, you get very low marks for project management, because that means that, you know, Git is a way for me to track when you're working on your project and when you're not working on your project, okay? So I'll see whenever you're working on your project, you do a check-in. It's great. If I see 10 check-ins, I know that you've managed your time well on this project, right? Due to be demoed on the 19th of January. So that's the first week we're back after this Christmas assignment. And here is the thing. Now, I know there was some... I wasn't totally happy with the marking scheme for the first assignment, okay? So I spent a good bit of time. I try and do these for every assignment. This is what's called a rubric, okay? So you look at this rubric very carefully. Everybody study it. And I'm hoping that you'll be able to judge and grade your own assignment and come up with the same mark that I come up with. This is what you need to include to get the different categories of marks. So in order to get it first, now first is 70 plus. The more things you have in this box here, the higher the mark you'll get. To get 80 plus, you need to have lots of stuff that's in that box, okay, for the first. So first of all, it looks great. It's all the art is your own or 100% procedural. In other words, you've got algorithms to draw everything in your program. There's significant amounts of clever animation or gameplay if it's a game. You know, you have multiple modes or screens. The assignment has lots of functionality. So, you know, power-ups, progression, that sort of thing. There's depth to the gameplay. The code is organized into classes. So it's not just in one big processing sketch. You've made classes for everything that appears on the screen. And you use inheritance and polymorphism. So in order to get it first, you've got to have inheritance and polymorphism. There's lots of novelty and originality. All the code is written by you. You've used PVectors. So we talked about PVectors in the class on Friday, and the second half of today's class is all going to be about PVectors. Transforms and classes. Your classes are all autonomous. So if you've got some character movement, that's all stored in the character class. Okay, so it's all autonomous. You'll be loading content from text files. You'll have used Git extensively. Everything works. And an example of that, I'll show you some examples of projects last year that got it first. Maybe if you do something like a twin stick shooter, to use both joysticks to control the character in the game, that's clearly a first if you achieve all of those other things. Now everything that you include in there, right, if you don't have everything in there, you can still get it first. But the more things from that box that you include in your project, the higher the mark you're going to get. If you want to get a 2-1, which is between 60 and 70, your project must look good, but it doesn't have to look spectacular. There should be some animation or gameplay, there should be a good effort. Some features might not be complete or entirely working. So in other words, it's not going to be perfect. There might not be file I/O, but of course there should be while loops, for loops, if statements, etc. Control aspects of the assignment. You might have classes, but you mightn't have bothered using polymorphism or inheritance. Maybe you use Git to do a few commits. And I'll show you a project which is a simple space shooter that one of the students did last year. which is between 60 and 70 marks. So that's what you need to aim for. You know, if your project is, you've got classes but no inheritance polymorphisms, it's fairly simple, but it's more or less all there, and it looks okay but not outstanding, then you get a 2-1. To get a 2-2, which is between 50 and 60, project is just looking so-so, but it's pretty basic. Should be some animation or gameplay, but maybe significant issues that you couldn't resolve in the project. You might have used sprites instead of drawing everything. All the movement and animation code will be pretty basic. So in other words, maybe colors changing or simple variables that you update the positions. You might not have used PVectors. There'll be no, I can't remember what I did for control code, but not a huge amount of code, maybe a page or two. And an example of something which will get a 2-2 would be a simple Pong game, a very basic Pong game with simple collisions, which is really easy to do. You could do it in a couple of hours, right? To get a pass, all your code in one file, around 100 lines of code, looks like it could be completed in an hour or two, mostly drawing, little or no control code, little or no functionality, lots of code acquired from other sources. And an example of something that will get a pass would be something like you tried to do a Pong game but didn't succeed, and that's an example of something that will get a pass. And obviously a fail then, something very basic that looks like it could have been completed in an hour, just drawing code, no control code, there's very little interactivity, and there's significant unaddressed technical problems. So that is your rubric for the assignment. So hopefully, I don't know, I tried my best to try and make it clear what I'm looking for in this assignment. Does anybody want to ask any questions about the rubric? Yes?
If I may, only because you said so yourself at the start,
Yeah.
what was it that you weren't happy about the other marking scheme?
Oh, just that I don't think I put enough detail in, so that I didn't give you something to aim for. I just said 50% for doing the core and 50% for extra stuff. What I should have done is said you get 5 marks for doing bullet power-ups, you get 5 marks for doing these things, to be a bit more explicit about where your marks were being allocated. What I did for the first assignment was I took a look at the extra functionality. I actually had written for the lab supervisors a list of different things that if you had implemented them, you would have got a certain number of marks. I should have made that available to you so you knew yourselves what you were going to get marks for. So that was my feeling for the first one. Even though I'm still happy that everyone got a fair mark, and I like to hope that you all feel you got a fair mark, you know. But and similarly, if anyone wanted to question their mark, I'm available if anybody wants to discuss a mark. I told you that, you know, for that time you could have come and asked me about it. But I personally feel I prefer this style, you know, where I tell you these are the things. If your project has these things, you're going to get it first. If your project doesn't have these things, you're going to get a pass or a 2-2 or a fail. So hopefully it's clear to you what you need to aspire to in order to get the different categories of marks. By the way, I'm open to suggestions. If you feel I should improve this rubric, you know, just tell me. If you think there's something that's missing from it or is not terribly clear from it, then please tell me and I'll update the rubric for everybody. Is that okay with everybody? So similarly, you know, if you use lots of Git and lots of check-ins and stuff, you get it first. And I should have probably put Git into the other categories there as well, but I will do. I'll put Git in. For example, you know, 2-1 or first, you must use Git in order to get those kind of grades. To get it a 2-2, then, you know, if there's no Git, then it's probably, you know, in that category there as well. Okay? So that's it. That's the assignment. Does anybody want to ask me any questions? Yeah.
When you say you want us to do all our art ourselves, is that also include music and sound effects?
Oh, good one. Oh, thank you. Thank you. I must have forgotten to collect it. Huh?
Music and sound effects, we have to do those ourselves?
No, but I'll tell you what you can use. You can use a thing called PVectors. Has anyone used PVector? So this is where I make all my sounds, right? Sound is just something that some people are either good at or not. And but you can make sound really easy if you just do a Google search for free game audio. This is where I get all my audio. Huh? Here we go. This is where I make all my sound effects for every game. And technically, I've made them myself because I come onto this website and I think, okay, I want a laser sound. You just click laser there. Why is there no sound here? Normally you can hear it. Okay, I'll reload the page. I don't know why it's not playing. Okay, say I want a laser sound. You just click laser and it gives you a random laser sound. And here, I'll plug this in now. And if you don't like that when you just click laser again, and you get a better laser sound. And then once you find one you're happy with, you just click Export WAV, and there you go. That's your laser sound. That's how I make all the game audio. But you know what? If you're really good at doing 8-bit audio, or you like making electronic music, or you're great at the guitar, why not record a piece of music for your game? Alright, so you'll definitely get marks for that as well. But it's not essential to do your own audio. But if you're good at it, definitely do it. Okay? Yes?
What was the name of that program again?
It's called PVectors. If you do Google search for free game audio, it's the first link that comes up. Or it's, it's on the first page, I should say. It's called PVectors. Alrighty? And you can use it to make lots of, all my game audio comes from there. If you want a jump sound. You can make lots of really cool 8-bit style sound effects there. Alrighty, is that okay with everybody?
Can you do more with that, like actual songs to play or anything?
Yeah, you can. Not using this program. This is for special effects. But yeah, if you want it, by all means, How many people? Does anybody here make music on their computer? Cool. So yeah, make music for your games as well. Okay, and I'll give you credit for it, and I'll put it up into the marking scheme. That's one of the things that will distinguish your project as well. If you make your own audio, but it's not essential. Okay. Alrighty. Your lab test tomorrow. Does everybody know you've got a lab test tomorrow? Okay, so just to be clear about what you need to know how to do tomorrow, you write this down, everybody, will you? And don't let me down. I want everybody to get 100% in this lab test, right? Whatever you need to do today, if you need to do a bit of cramming today, then do it. Just make sure that you know what you need to know for this lab test, right? Number one thing, how to load a file. And I don't mean an audio file or an image file, I mean a text file with some data in it. So the lab you need to look at is the TunePal Data Lab, okay? So study that lab before tomorrow's lab test. And you need to know how to make classes. And then obviously all of the sort of programming stuff, like just doing sort of line, circle drawing, all that kind of stuff. And you need to know how to do things with arrays, array lists. Array lists, definitely. Make sure you know how to get something into an array list, get something out of it, get the size of an array list, iterate an array list, and then just generally do things with algorithms in an array list, like add and remove elements and count things and calculate averages and things like that. Okay, that's what you need to know for tomorrow's lab test.
You're not going to put in vectors, are you?
No, I don't need vectors. And I don't think there's any, at the moment there's no trigonometry on it. It's just a little simple algorithm that you have to construct. And I want everybody to get 100%. So don't let me down. Do whatever you have to do. Do whatever you have to do today. Study what you need to study. Okay? If you're not too sure about how classes work or how to do, some drawing or whatever, make sure you study it today. Okay? Yeah.
We're not going to do unit circle.
No. I actually I had planned to do a more complex one, and then when I did the solution myself yesterday, I found that I got up to a certain level and I thought this is probably enough. So, yeah. So there was a thing I was going to include which required you to do some unit circle stuff, and then I decided not to include it. Oh yeah, I'll show you the little assignment framework code, okay? It's nothing terribly fancy, but it doesn't do anything terribly interesting.
Will tomorrow's lab have an attendance multi-choice question as well?
Tomorrow's lab?
Yeah.
No multi-choice question tomorrow, just a lab test. Yeah, here's your assignment starter code, okay? This is up on the GitHub as well. And there's just a very simple, the main purpose of this assignment starter code, the Yask project that we're making, the game that we're making, I'm going to put that's up on the GitHub. Anyone that wants it can look at that, okay? There's lots of examples. But this is your assignment code, and I just made a simple class called player. It has a p-vector for the position, and then there's a character for up, down, left, right, the start button, because there's a start button, player 1 start and player 2 start buttons. And then there's a button 1 and button 2, which are the buttons beside the joystick you can hit, okay? And index is nothing. Index is just a number to say what player we're talking about, and color then is just the player. So, if you want to look, the most important keys, the most important thing here is, also this project has the ability to check multiple characters, multiple keys, key presses at the same time. So there's a method here called check key, and you pass in the character of the key code that you're looking for, and it will tell you whether it's pressed or not. So that just tells you whether the up key, whatever the up key is mapped to, is pressed. Because up, see the parameter there? That's just a character, so that could be anything. Alright, and in fact that's loaded from an XML file. And you know, when you press the start key, it just prints out the test player, index, start, and player 1. So this is just to do with the buttons really. And I'll show you what the XML file looks like. Yeah, so in the data folder you'll see there's just a little XML file there. And it just looks like this. You know what XML looks like? It's just this hierarchical format. I should probably turn the light on here a little bit. So that's what it looks like. There's just a player tag, and inside the player tag it's telling you what key is mapped to the up behavior, what key is mapped to down, what key is mapped to left and right for the first player. Because there's two joysticks, there's two sets of controls on the arcade cabinet. So it just tells you what keys. The reason why I did this is because I haven't quite figured out how to change the key bindings. They're hardware things which are mapped up to a little hardware microcontroller, and it's quite tricky. Myself and Keane spent an hour at it, or several hours at it last Tuesday, and couldn't figure out how to do the key bindings properly. So I'll give you this file. I'll give you a later version of this file when we're putting them onto the actual machine. You can use this for development, and then when we're putting it onto the actual arcade cabinet, I'll give you a different file. Okay, and then it will tell you what the actual key bindings are. So anyway, at the moment, W, S, A, D, Q, 5, E, and R, and then these are the keys that are mapped, you know, for the left, for the right-hand player. And what this program does is it goes and loads up that XML file. You can parse XML and processing really easy. And then it constructs the players based on that XML file. You can have a look at this yourself. I don't want to spend too long on it because it's not important. All it is showing you how to get the key bindings. And this is just code you can use in your assignment to get started. And when you run the assignment, basically you just get this, not terribly fancy, just two players on the screen like that. One is controlled using the left-hand player. See, I haven't even bothered updating the screen, you know, clearing the background. So one is just controlled using the W, A, S, D keys, and the other is controlled using these keys here. And then if you press like the keys that are bound, player 1 start, player 1 button 1, player 0 start. It just prints out in the bottom there if you press the start key. The start key I've currently mapped to Q, for example. So when I press Q, it thinks that it's the player 1 start key. Alrighty, that's your assignment starter code. Yeah, so take the time to have a read through it and make sure you understand it in your own time. It's not very complicated. All it's doing is just mapping those keys onto things like the up and the down, whatever, and that's what you use to control your player. Is that okay with everybody? So I've done loads of talking, and I don't like to do too much talking in my lecture. I prefer you guys to write programs. So I need to do one more bit of talking. Let's talk about vectors, because I'm finished with the assignment now. Unless there's any other questions about the assignment. So a great way to get started on your assignment would be come to the game jam this Saturday and make a game for 12 hours with me and all my other gamey friends. It's your choice. Okay, come, it'll be great. Okay, so we talk about vectors. There's a few like the last bits of the course that I want to kind of wrap up before we finish. So the first one is vectors, which we started talking about on Friday. Is everybody okay? Ready to move on to the next thing? Hello? Just say yes, okay, if you're ready. Okay, cool. Let's talk about vectors. Right. You all like the assignment?
Yeah.
How many people like the assignment? How many people think it's an awesome assignment? How many people are really looking forward to getting started on the assignment? Me too. If I had an assignment like that to work on when I was in college, I think I I just would have exploded with happiness, right? I'll tell you something that strikes me about this class, right? When I was a little boy, I used to have a dream that I owned a rocket ship. It was a toy that I wanted to have, and I was obsessed by this rocket toy. And I used to actually have dreams that I owned this rocket. And sometimes I would wake up, and I knew I was waking up, right? Because I'd hold on to this rocket toy that I really wanted to own. And I would think if I held on to it closely enough, if I held on to it tightly enough, when I woke up, it would still be there when I woke up. And of course, it never was. But you know what? What we're learning on this course, if you think about what we've been doing over the last few weeks, we made a little rocket ship. So now you can actually take the rocket ship, and if you want it, you know how to make it. You can make it yourself, and you can make it shoot. I mean, it's awesome. I think programming is just the most wonderful thing. There's nothing else in the world, not engineering, not any amount of chemistry, where you can literally have an idea in your head, and a few hours later, you can make a thing, which is a thing. You can make the thing you had in your head. There's nothing like it on Earth. I even think about polymorphism. Polymorphism, there would be no internet without polymorphism. There would be no iPhone without polymorphism. There would be no games. There would be no apps. Polymorphism is at the heart of almost every piece of software in the world. What percentage of people in the world do you think know how polymorphism works? I would think it's very much less than 1%, or a fraction of 1% of the people in the world know how polymorphism works. But you know what? You guys do. So you're part of a very, very exclusive club of people in the world who know how things work. I think that's amazing. Don't you think that's amazing? Yeah, I think it's amazing. Okay, so let's talk about vectors. Okay. So when we're moving things, and the way we've been moving things up until now is just by changing the x and y components. The x and y position where we're drawing something, and we're changing that just by adding something to the x and adding something to the y. Right. So there's a mathematical concept which will really help you to make much more impressive projects. By the way, equally this applies whether you're doing an iPhone app and you need to do some animation to swipe away one of the screens or whatever. This is equally applicable. So don't think this is just exclusive to games. This is actually essential for you to make any kind of program with a user interface. Okay? They all use vectors. So we know the origin of the screen is up in the top left-hand corner there, isn't it? So that's the position 0, 0. Let's imagine that I have something in my screen, in my program, and I'm going to draw it at some position over here. Let's just make up a position. Let's say that's over 10 and down 10. Okay, does everybody understand what those numbers mean? Alright, so we might imagine then that I want to move this to another position. I want to move it to a position over 20 and down 8. Let's pick those two numbers there. Alright, so what would I need to do to this to make it move to this position here? What would I need to add to it? What's that? So you'd add 10 to the x, wouldn't you? And you would take away 2. So how did you know that? Yeah, but what did you do to work out those two numbers? So you subtracted. Okay, cool. So, yeah, so I know that if I want to take this thing at 10, 10 and move it to 28, then there's something that I can add to this one to make it into this one. And the way I worked that out was by taking this one and subtracting this one from it. Is that okay? That's exactly what you did. You took the 20 here and you subtracted 10 from it. You took the 8 here and you subtracted 10 from it and you got -2. So you worked out what you needed to add to this one by subtracting this one. So anyway, I can see that there's some other thing. And that other thing is equals to 10 minus 2. That vector 10 minus, that set of numbers 10 minus 2. Okay? That's what you need to add to this to make it into this. Is that okay? And, okay, so the next thing is, the whole concept of a vector is that instead of like looking at what you need to do to the x and what you need to do to the y, instead of treating those separately as two numbers, instead we group them together into this mathematical concept called a vector. And a vector is just a list of numbers. And I see that this is just a list of numbers. It's a list of two numbers, but this is a list of two numbers as well. So that's what a vector is. A vector is just a way of grouping those two numbers together into one thing called a vector. So I've got 3 vectors here, and I can say certain things about them. If I have the vector, if I group this thing and this thing into here, there's one operation which you've already discovered, and that's the ability to subtract one vector from another vector. And to subtract one vector from another vector, what do? You subtract the x's from each other, and you subtract the y's from each other, and then that gives you the vector, the resulting vector. So, I could say if I call that one A, and I call that one B, and I call that one C there, alright, then basically that just means that I'm grouping these together. How I calculate C is I go C dot x is equals to A dot x minus, B dot x minus A dot x. And then C dot y is equals to B dot y minus A dot y. Is that okay? That's exactly what you just did, isn't it? Alright, so another way of writing this, instead of writing this as two steps, you can just go, by the way, this assumes that A and B and C are classes or something that have x and y components. In other words, the actual list of numbers is stored in things called x and y. Alrighty, so anyway, you can also say C equals B minus A. And if these guys are vectors, and in a lot of maths books you'll see them written like this with little arrows over their head like that. And that means that they're vectors. By the way, you guys should be all taking notes on pen and paper. So when you write C equals B minus A, that means this. It means you subtract the x's from the x's and the y's from the y's, and that gives you this other thing. So does everybody understand how to subtract vectors? What it means?
Yeah.
Another interesting thing, right? See this vector C here. If you look at this vector C, 10 and minus 2, you know, its origin is not the origin as such. Sure, it's not. Its origin is actually A, isn't it? Because if I add it to A, I make B. So they're all relative to something. But you can also draw that vector up here. So there's the vector 10 and minus 2. The vector 10 and minus 2 is going to be that vector. So that's going to be over 10 and down minus 2. That's the actual vector drawing. And that's the same as this vector. They're exactly the same. So I've just taken B minus A, and you can see if you draw that in up there, it's the same as the vector B minus A. Everybody see that? It's the same length, it's the same direction, it's pointing in the same direction. So, the next thing, if I wanted to calculate the distance from A to B, how would I calculate that? And those of you that are here on Friday might remember, but those of you that weren't here on Friday might think about it. How do I calculate the distance from A to B?
Using the formula?
Yes, so what is the formula? The distance from point A to point B is given by the formula
y2 minus y1
yes. y2 minus y1
squared
squared
plus x2 minus x1
squared. Okay, that's how you calculate. You guys might, I'm sure you all, how many people have seen this before? Is there anybody who hasn't seen this before? Cool. I bet you all have seen it, but maybe, just not used it for a while, okay? Again, those of you that were here on Friday will know the answers to this. Those of you that weren't here on Friday, why is that the way you calculate the distance between 2 points? It's the triangle. It's all to do with the right angle triangle. So let's take A and B there, and let's make a right angle triangle out of it like this. Okay, there's a right angle triangle just like that. I'm just drawing a horizontal line there and a vertical line down there, and then that becomes a right angle triangle. We remember the right angle triangle. I'm going to use lowercase letters. If I call that H, we call that the hypotenuse of a right angle triangle. And if I call that A, lowercase a, and that's B, I can say that because the theorem of Pythagoras says that H squared equals A squared plus B squared. Okay? So that means the square of the hypotenuse is equal to the sum of the square of the other two sides. Right? So H squared equals A squared plus B squared. Or if I do the square root of this side, I'll get H equals the square root of A squared plus B squared. Now you can see that these are already starting to look pretty similar, aren't they? This is the square root, the square root. So then let's look at how we would calculate A. How would I calculate the distance there, A? It's basically the horizontal distance. How would I calculate the lowercase a distance? What's that? Yeah, you can see that it's going to be 20 minus 10, isn't it? the distance there has to be 20 minus 10. So it's going to be this x guy minus this x guy. So it'll be 20 minus 10. 20 minus 10 is the same as saying x2 minus x1, isn't it? It's the same as saying take one of the x's, x2, subtract this x here, x1. So it's the same. Alright? So then we can replace a with x2 minus x1 to be squared. And the same for the lowercase b. So lowercase b is going to be, it'll be y2 minus y1. So it'll be this guy's y minus this guy's y. It's going to give me that distance there. Plus y2 minus y1 to be squared. And then we get the square root of it. And that's where that comes from. An interesting thing, right, which I'm sure you've probably realized as well, the distance here, right, is the same as the distance here, isn't it? Because it's the same vector. Can everybody see that? That the b minus a, when I plot c up here, it's the same as this vector. Can everybody see that? That this distance is the same as this distance. Okay. So, I could drop my right angle triangle down there, and I could calculate this distance. You know, and then I would also know the distance from the vector A to the vector B, wouldn't I? So how do I calculate this distance? This is even easier, because this is going to be x2 minus x1, so it'll be 10 minus 0, and minus 2 minus 0. So you can just say it's going to be the square root of 10 squared plus minus 2 to be squared. So that's another way to calculate the difference between A and B, or the distance between A and B, is to take the vector C, which is the same as saying B minus A, and then calculate the length of C, and it's the same as the distance. Does everybody see that?
Yeah, but C is the product of A
Yes.
and B, so you're doing that thing anyway.
You are, exactly. Yeah, the reason why I'm showing you that is just to show you that they're equivalent, that they're the same. So there is, in fact, a thing to do with this way of calculating this distance, and this is called the length of a vector. So the length of a vector is given by the distance from the origin to that vector. That's the length of a vector. So the length of a vector, which you can derive from this, is equals to the square root of the x squared plus the y squared. And that's called the length of a vector. So what have we learned about vectors? First of all, you can add vectors together. Second of all, you can subtract vectors. Finally, you can calculate a thing called the length of a vector. And the length of the vector is equal to the square root of x2 and plus the square root of y, square root of the x to be squared and the y to be squared. So there's three things we can do with vectors already. And we all work that out. Everybody's following all of this? Cool.
Right.
Yes.
What actually is a vector?
What is a vector? It's a list of numbers. So in this case here, it's a list of two numbers, and we call those numbers x and y.
Okay.
Is that clear? Is that okay?
Yeah.
Cool. So we can add, subtract, calculate the length of vectors. Here's another thing. Say I was to take this vector here, right? This vector here, which we call C. And say I take the vector C and I double it. What will that have the effect? If I started at A and I calculated B minus A and then I multiplied it by 2, what would that have the effect of doing? If I started at A and instead of adding C to A, I added C multiplied by 2 to A, where would I end up? Well, I would go as far as here, and then I would go the same distance again. Can you see that? So if I take C and multiply by 2, I'd end up over here. So that's called scaling a vector. And that means multiplying each component of the vector by a scalar, or a float. So you can also multiply a vector by a scalar. And you can clearly see from this diagram, what effect does it have on the direction of the vector? None. It goes in the same direction after you scale it, but it goes, you know, a longer distance, right? And that's called scaling a vector. Multiplying a vector by a scalar. Adding, subtracting, calculating the length. Yeah. Cool. It's almost 11 o'clock, right? So I think it's almost time to take a break. But before we take a break, because I want to write some code after this, I'm just going to introduce you to a new class in processing. And that new class in processing, which will do all of this stuff for you, is called a PVector. So the PVector is a class, right? So you can go PVector P for position equals new PVector. And you get something that has an x and a y component. there are methods on the PVector class. So for example, you can do p.add with a lowercase a, and you can pass in another PVector in here, and it will add that PVector to this PVector. You can also do PVector.sub, and it will subtract. You can do PVector.length, which I think is called magnitude. But I'll need you just double check that. I can't quite remember whether it's magnitude or length. And that will calculate this value here, which is called the length of a vector. And then to multiply a vector by a scalar, you can go pvector.mult. And you can pass in, for example, 5, and it will multiply that vector by 5. Cool. What we'll do after the break is we'll start refactoring our Space Wars game, and I'm going to replace some of the positions with p-vectors, and you'll see how you use p-vectors in code. But most importantly, that everybody understands what a p-vector is, what a vector is. Adding p-vectors, it's simple, isn't it? It's just you add the x's together and the y's together, calculate the length. It's just this formula here, but you're going to use a method in processing to do it. And then we'll see if we can replace some of our code with p-vectors. Okay, let's take 10 minutes.
Right.
Yes?
Maybe I'll send the coordinates then to that p-vector.
So you can use .x or .y to set them, or you can use the
Oh, cool. I just got it there. Oh, yeah.
Okay, everybody, here's the Space Wars work in progress that we've been working on in the class for the last few weeks. So, here on the screen. So, what we started working on Friday was going to the game object class, okay? And where we previously had it, this code is up on GitHub. If you want to get it, you can get this code. This is what we worked on Friday because it's incomplete. But if you remember, I had a game object base class, and then I had subclasses for big, star, bullet, and so on for the player and polygon that extend the game object base class, right? And in game object, I had a float for position x and a float for y. So now I'm going to take the game object and I'm refactoring it, so I'm replacing x and y with a p-vector. So now I've got a p-vector called position, and I'm just going p-vector position. Let's do semicolon here, and I will make it in the constructor here instead. So new p-vector. There's a constructor for p-vector that takes the x and y components. So you can go width divided by 2 and height divided by 2. So that takes the p-vector and sets the x component and sets the y component. Is that okay with everybody so far? So now p-vector is replacing where we previously had x and y. I'm going to put p-vector in there. I'm going to put one other p-vector in here. And I'm going to call this vector forward. So this p-vector is going to tell me what direction is forward for this particular game object, right? Now, quick question for you. Do you guys remember what's the forward vector for this we'll say for the player object? What's the forward vector for the player object? Would you think about it for a second? What do you think the player's forward vector should be? It should be up, shouldn't it? And what's up in processing? It's minus y, okay, and it's 0 on the x. Because in order to make something go upwards, we have to add minus on the y. So I'm going to make the forward vector for this equals to 0 and minus 1. Okay, so that's the forward vector. So think about it. If I wanted my we'll say the player, for example, if I want my player vector to go in the forward direction, I'm going to add the forward vector to the position. And that way it's going to move up. Does everybody understand that? Because that's the effect of subtracting something from the y. If I add those two vectors together. It's the effect of adding minus 1 to the y. Does everybody understand that? Okay, take a minute to think about what that means, right? And make sure that you understand what that means. If I add the forward vector to that position, it's going to move forward. And forward is going to be up for us. Isn't that right? Is everybody clear on that? Good. Let's move on then, okay? So I think pretty much this program is not going to compile just right now, but let me take a look at where I need to modify this thing. So now I have the player class, and you notice the player class here takes the x and y as a parameter here. Instead of going this dot x and this dot y equals that, I am going to go position dot x is equals to x, and position dot y equals y. Alright, so this is getting access to the x and y components. And I'm going to group the x and y components for the position into this vector object. So here's this other constructor here. We're just going to refactor everything so that now we're using the PVector. Cool. Alright, so there's the player. What else do I need to modify here? Let's get rid of
See that
this.
again?
Huh?
Until we get on to position thing.
Sure. All I've done, and I tell you what, if you take the Spaceforce work in progress code and you try and run it or compile it, because I've gotten rid of the x and y from the base class, it's no longer going to compile. Okay, because there's loads of times when I'm referring to the x and y. So whenever I have x and y referred to as being fields of the player class, instead I'm going to replace those with position.x or position.y, because now the vector is holding the position, and the x and y components are stored in the x and y components of the player. So, the vector. So looking at the display method now, right, so you can see that there's a call to translate x and y, so what will we do there? We'll replace that with position dot x and position dot y. So that's the drawing. The move code. The move code is interesting, right? Let's get rid of LX and LY. And where we had LX and LY, LX and LY, if you remember, what were LX and LY telling us? Can you guys remember? So I'm using the sine of the angle of rotation and the cosine of the angle of rotation to calculate LX and LY. So what's LX and LY now? What did we just make? It's the... What are we using that to tell us? We're using that, if you look down there, we're using that to tell us what direction we want the character to move. And we're using the theta value, which is the rotation amount, to calculate Lx and Ly. So Lx and Ly we're going to replace with the forward vector. So it'll be forward dot x is equals to the sine of the angle, and forward dot y is equals to minus the cosine of the angle. So I can show you how that works as well. I mean, this will literally take us a couple of seconds, but we've done it a few times, and maybe if I show you again, you might remember how this is going to work, right? And in vectors, it makes a lot more sense when you think about things as vectors rather than separating the x and the y. I have this field in the player class, which is called theta. And this is going to tell me how much my player is rotated by. And when I press certain keys, I'm going to add and remove some values from theta. So I have some amounts that I'm going to rotate my player by, and now I need to calculate what way is forward for the player. Okay? Based on how much rotation I'm applying. So the rotations, this is my character here. If I'm rotated 0, then that means my forward is straight up. Doesn't that make sense? Then I'm going to rotate clockwise in this way, and I want to calculate the new forward vector. So I imagine the center of my guy is at 0, 0. If I want to move straight up, it's 0 and minus 1. Fair enough? If I want to move straight down, it's going to be 0 and 1. If I want to move to the right, it's going to be 1 and 0, my forward vector. And if I want to move to the left, it's minus 1 and 0. Is that okay with everybody? We've done this a few times, so hopefully, you might remember it now, and maybe it'll make a bit more sense when we think about these as vectors. So these are my forward vectors. This is what I'm going to move in the direction of. And then I need to calculate this based on what angle I'm rotated by. So if everyone could just look up for a second instead of working on the code, right? Just think about this, and hopefully this is, again, you'll remember this. Here is my angle of rotation. I'm rotating now by theta radians, rotating some amount. And now I want to calculate my new forward vector. So the new forward vector, the algorithm we use is just to draw the line across there, make a right angle triangle out of this here. This then, the x becomes the opposite, and the y is the adjacent of that angle in this right angle triangle. Alright, so this is the x and the y of the forward vector. And the x is going to be the distance from there to there. Y is the distance from there to there. Okay? So I can say that the sine of the angle theta is going to be equals to the x component, and the hypotenuse is 1, because the distance from the centre there is 1. So x is equals to the sine of that angle, and y of the forward vector is equals to minus the cosine of it. Alright, why? Because y is the adjacent to that angle theta. I'm rotating by theta around that centre point there. There's the angle of rotation. Make a right angle triangle out of it. And you can see that the x component of the forward vector is made by the sine of that angle. The y component of the forward vector is minus the cosine of it. So we've done that about at least 3 times in the class. I don't mind explaining this to anybody, because as you might realise, I really love explaining things. But if anybody wants to ask me any questions about this, or if you're still not sure about why this is the sine and cosine, I can give you some very good, I recommend some very good videos from the Khan Academy which explains this concept. It's called the unit circle. Alright, yeah?
Link on the
No, or I'll link it on the GitHub, and maybe you just need to see it a couple of times more and you'll see immediately, yeah, it has to be the sine and the cosine. There's no, that's the way you do these calculations, right? So now I have my forward vector calculated in this way. Let's take this code here. You know, I'm going to take these 2 lines and I'm going to replace it with 1 line. So instead of going x equals x plus lx, y equals y plus ly, let's take this code and replace it with the vector code. So position dot add the forward vector. And then we'll replace this s, which is meant to be backwards, okay? So this should really position dot subtract. Is it sub? Yeah, so it's add and sub. So these are the methods we're going to use on the vector class. So you can go dot add forward and dot sub forward. Here we go. We do have to do something with the bullet class here. Now everybody look at the bullet here. What am I going to do with the bullet? You remember we made the bullet, and we did that lab where we made the bullet. What am I going to do with the x and y of the bullet? Have a guess, if you're not too sure. What am I doing currently? I'm assigning the x's and the y's separately. What should I do instead? They're in a PVector then. They are already in a PVector because bullet extends the base class. So bullet extends the base class, so it has a PVector position. I'm going to make a deliberate mistake here, and maybe you guys will see it. First of all, what are we doing with the bullets? We want the bullet position to start at the player position, don't we? So I'm going to start at the same position with the player. So how about this? Does this look like it makes sense? Right? Instead of doing this, does this look good? Bullet dot equals. Alrighty. Does that look okay? Does that make sense? How many people think that makes sense? How many people think it doesn't make sense? Why does it not make sense? How many people didn't put up their hand for either of the 2 above? You have to put up your hand for something. Okay, why did you not put up your hand?
Oh, I don't answer that. I'll answer something else.
Go on.
It looks appropriate, but it just seems too convenient.
Sure.
Yeah.
Yeah, cool. I tell you what, let's leave it as is, but I want to make sure everybody understands. Like, I don't care if you think it's right or wrong, but I want you to understand what our intent is. Our intent is to take the player's position, create a bullet object, set the bullet to be the player's position. So it starts at the player's position, and then it's going to go off and do its own thing. The player can move off, and the bullet has a position, which starts at the player's position. Does that make sense?
But I don't know what's going on with these position and the other variable thing you're using.
Which other one? Look, with the forward one, was it?
Yeah, don't know what they're doing.
Okay, so I'll tell you what, right? Let's take a look at the forward one, okay? When I press the W key, what I want to happen is I want my player to move in the direction of the forward key, okay? So you have to imagine if I have no rotation applied to this, what's going to happen here is I'll take its position and subtract 1 from the Y, because that's what we were previously doing. We were just subtracting 1 from the Y. Is that okay? Because I want it to move upwards if I press the W key. But now because I'm rotating it, when I rotate it, I want it to move in the direction in which it's rotated by. Is that okay? Does that make sense, Darren?
No,
Yeah?
I just don't know what they're actually are. Like, I'm still not sure what these vectors are actually doing to it.
Sure. So let me give you a scenario, right? Say I wanted to have a simple, character in my game. Let's say it's just represented by a cube, right? And let's say I have a p-vector which I'm going to use to store the position at which I'm going to draw this, right? So that's the position there. And say this is going to be stored in a p-vector called position. So at a later stage, I'm going to do something like rect position.x, comma position.y. Like that, and then we say 10, 10, like that. Alrighty, does that make sense so far? So I take some position vector and I go rect position.x, position.y is 10 and 10. Okay, so I'm just using the x and y to control the position at which I'm drawing it. If I had some code in there and I was going position.x plus x plus equals to 1, and I had that inside my draw code, what would happen to that rectangle?
Over.
It would move over from the left to the right, wouldn't it? Does everybody understand that? Okay, if I went position.x minus equals to 1, what would happen?
Left.
It would move left, wouldn't it? If I had position.y plus equals to 1, what would happen?
Move down.
It's going to move down, and position.y minus equals to 1, and it would move up. Is that okay? You happy with that? Cool. So that's all I'm doing here. When I go position.add forward, that's exactly what I'm doing. I'm just saying whatever value forward is. By default, forward is 0 and minus 1. Okay, so if I don't rotate this right, then it's going to move in its forward direction, which is straight upwards. Is that all right? If I was to say, when I calculate that sine and cosine thing, I'm calculating the forward vector based on how much I'm rotating it by. And you can see the keys there. When I press A, if you have a look at the code there, what happens when I press A? What direction will it rotate? It'll rotate to the left, or it'll rotate to the right, because I'm increasing the value of theta. So, when I'm adding and subtracting the forward vector, actually this isn't going to change the behavior even slightly. But let's just make all my code compile now. Instead of doing that for the bullet, let's get rid of that. And basically what I'm doing is taking everywhere I have two components, I'm going to replace it with the p-vector. Forward.x is going to be equals to the sine of theta equals minus the cosine of theta. And I'm multiplying it by speed. Let's not even do that for now. Comment that out because there is a slight little couple of twisty things here that we need to do. And this is my wraparound code. I'm going to get rid of all this wraparound code because it'll just take too long to refactor. Let's not worry about the bullets. Let's just make everything compile for now, right? So instead of polygon this and x, I'm going to replace it with position. Okay. So I'm going to translate position.x. Big star, let's do the same thing here. If you guys have the code there, you can work along with this as well, okay? And refactor everything to make it compile. Replacing everywhere you have x with position.x, and everywhere you have y with position.y.
Will you put this on the GitHub later?
Of course, yeah, sure.
I think I'm just too behind to just get it later.
No probs.
Alright.
Yeah,
Why are you declaring the forward vector?
I declared it in game object. So let's see if everything will compile now. Okay, so the bug also has position.x. And then when I'm doing translate, I just replace it with position. And there's position. position dot y.
When you're doing display, would you want to change it as well? When you're drawing them in the main method.
Yeah, say again.
When you're drawing them in the main display method.
In the display method on the objects or in the display method
main.
here?
There. Would you
No,
want to
because
change it again?
when I call display, I don't need to make use of the x and y. It's inside the method that the call is there. Okay. So let's try. Oh, where's that? Let's just fix all of this. Oh, it should be feet. Okay, the last place where we need to translate position dot x and position dot y. That should be bullet position equals position. Awesome, everything is now compiling. Okay, so just to be clear about what I did there, okay, all I did, which is to change this program from the last program that we looked at a week ago, was I replaced x and y with position.x and position.y, and I replaced where I declared them as floats with a p-vector. Does everybody understand that? Is everybody okay with that? Cool. Right, now we have the thing of the bullet. Alright, let's take a look at our bullet code here, because there's two kind of gotchas, right, that I want to explain. Here's the player. There's bullet, player.position, bullet.position equals the player's position. That kind of makes sense, doesn't it? How many people have their code up to this level? Or does anyone have something which compiles? Is anybody working along here? Yeah, okay. So keep typing along, okay, and then run your program and tell me what happens when you fire a bullet. Maybe pause the video and I'll give you 10 minutes to try and just catch up. So assuming everybody knows, what we've done is taken x and y, instead we're going to group it into another class called position. And we have something which tells us which direction our spaceship is pointing. We've got the forward vector, right? So, again, looking over at player. We think this kind of makes sense to go bullet.position equals the player position. So that's going to set the initial position of the bullet to be whatever the player's position is going to be. Is everybody kind of happy with how it's working? Okay, let's try and fire a bullet now and see what happens. Now, I'm not exactly sure what's going to happen, but I know it's not going to be what we want. First of all, there we go. I'm able to rotate. My p-vector x and y component is calculated from the sine and cosine of the angle of rotation. And then I press the space key to create a bullet. And look what happens. So clearly something is wrong. Well, let's see. Does it add? Let's have a look at my bullet. There's the forward x, the forward y. Okay, here's the thing I haven't done in the bullet. You're right, so I'm not doing the bullet update. Let's do the bullet update. So that should be position dot add the forward vector, and we won't worry about the speed for now, okay? You're right, because I commented that bit out. So let's try it now. Here's my bullet move code. Here's my player. I'm pressing the space bar. Oh my god, what's happening? Okay, so look at what's happening, first of all. Look, if you can even see on the screen.
If you keep pressing it, just gets really, really fast.
Yeah? You got that?
Yeah.
Okay. Can anybody see what's happening? Can you kind of figure out from looking at what's happening?
Create the coordinate sticks to the ship.
The bullets are sticking to the ship now, aren't they? Can you see that?
Are you using the same vector for both the ship and the bullet?
Well, am I? That's the question.
Is it the base class vector?
Yes, I am using the same vector for the bullet and the player. Why am I using the same vector? Where's the code where I say use the same vector for the bullet and the player?
The bullet position equals player position.
Okay, exactly. Remember what happens, because these are objects, guys, because these are objects, remember what happens when you do an assignment from one object to another object. So I have the player over here. The player has got a position p-vector, okay? This is the player. And then the player goes and instantiates a new bullet instance. So now I have the bullet instance over here. And this bullet has got a p-vector, because it creates one in the constructor for the bullet. PVector. Okay, so now these are two separate objects, so there's two separate p-vectors. Look at the code. When I go player.position equals, bullet.position equals position, what does that do? What that does is, like, actually I'll just write these into separate objects. This is the bullet pos for the bullet, and this is the player position over here. When I go bullet.position equals the player position, this takes the bullet's position vector, and instead, watch what I'm doing, everybody look at this very carefully. What happens here is, it takes this, and it makes it now point at this object, and what happens to this object? Garbage collected. So now the bullet vector and the position vector are actually referencing the same object. It's like a pointer. Remember that? Remember I told you that's what happens when you copy one object or you assign one object to another object. Does everybody understand now why this is a problem or what has happened? Exactly. So what I need to do, and if you wrote the same code, very interestingly, in the language C#, this would not happen. If you wrote this in the language C++, this would not happen, because C++ and C# have a concept called aggregate value types that Java doesn't have. What we need to do is, instead of taking the reference and updating the references, what I need to do is make a new, or copy the values from one object into the other object. And there are two ways to do that. But here's the way that is kind of recommended. And unfortunately, there's no logic to this, okay? It's just something that you need to remember. If you get these kind of errors in your program, this is how you fix them. Instead of going bullet.position equals position, you do position.get. And get is a method on the PVector class. And what that will do is create a new PVector with the values of the old PVector. Alrighty, so it keeps them separate.
Is that so? Bullet position will reference that new one.
Yes, exactly. So the bullet position, old position gets thrown away, and you get a separate object for the bullet position, which has copied its values from this one. So .get, and that's because this is based on the Java language, and this is how you have to do things in Java. That's just a limitation of it. Similarly, you know the way we're able to write something like P equals P plus V. You know, we're able to say position equals position plus velocity. You can't write that in Java. You have to go .add. But in other programming languages, they support a concept called operator overloading, where you can change the behavior of the plus symbol. But Java doesn't support it. So now when I do .get, I rotate here, they are separate. It keeps them as separate objects. So that's the PVector get. So we've exactly 9 minutes left. That's one very important concept that you have to understand with PVectors. Lots of the times you have to remember, when you do an assignment from one PVector to another PVector, all it does is update the references. If you want to take the values from one PVector and make them the values of another PVector, the best way to do it is to go .get on the PVector that you're going from, and then you'll get a new PVector. Is that okay with everybody? That's problem number 1. Problem number 2 is here in bullet. And it isn't really a terrible problem, and there's actually loads of nice solutions to it, right? The problem is that the bullet now has no speed. It's always moving at a speed of 1, because I'm always adding the forward vector. The forward vector is always of length 1. So if you imagine if I take the position and I subtract 1 from the y, it has moved 1 unit. So I'm always moving exactly 1 unit here. What I want to do is take the forward vector, multiply by the speed, and then add to position. So what you can do here is you can go forward.mult the speed. So this was the scaling thing that I talked about earlier. Okay, so you can go forward.mult speed. So that takes the forward vector and multiplies it by the speed. So the forward vector currently is just going to add 1, you know, and then if you multiply by the speed, it will make it go 10 times as fast. So now I get I get my bullets going at a speed of 10 rather than a speed of 1. Can anyone see any problems with that code? It's more of a conceptual issue rather than an actual practical thing, because as you can see, it works fine. But is there anything that is happening there that we might not want to happen? What happens to the forward vector when I go multiply by the speed? Does it change does it change the size of that vector? Yes, it does. It changes the vector. So I'm going to take the x component of the vector, I'm going to multiply by the speed, and I'm going to take the y component of the vector and multiply by the speed. That changes the forward vector so that the forward vector is no longer of length 1. So that's a problem, right? So what I want to do, for example, is multiply the speed, multiply by the forward vector by the speed, but instead of changing the forward vector, get a new vector. Alright, so I don't want to change the existing vector. So actually, when you call .mult.add, there's two versions of those, okay? Or add, subtract, and multiply by, there's two versions of them. If I want to get a vector back without modifying the forward vector, in other words, you can write this code instead. So let's call this velocity. It's going to be equals to, and you write your code like this, PVector.
Could you not go forward.get and then in brackets forward
Totally.
.mult?
That's another great way of doing it. Definitely. Brilliant. I'm really impressed that you figured that out as well, right? This is another way to do it. And you'll find that sometimes it's just neater to write your code in this way. Sorry, go ahead. PVector. .mult. Okay, everybody look at this code for a second. It's really important. If you remember, the previous point here was that when I just go, forward.mult, that's going to change the forward vector size of the forward vector. All right, it's going to multiply each component of it. But I don't want to change the forward vector. A way you can do it is by using this way of calling .mult. So you do PVector.mult. This is an example of something which is quite hard to do in processing yourself. But when we do Java next year, you'll discover that Java has a way of writing methods which run on the class rather than an instance of the class. And those methods, does anybody know what they're called? I guarantee you, and you can write this down now, I am going to ask you this question in your summer exam. It's on your summer exam. Give me a definition for a static method. It's called a static method. And it's a method that operates on the class rather than an instance of the class. So there's static versions of all of these .add, .mult, etc. When you go PVector.mult, you pass in the vector you want to multiply. You pass in what you want to multiply it by, and it returns you a new PVector. So in other words, forward doesn't get changed, but you get a new PVector out of it. So there's static versions of all of that. Now, Daniel Shipman, who wrote the processing book, has written a great book all about, it's called The Nature of Code, and he's a fabulous chapter on it, all about PVectors, which go into a little bit more detail about this stuff today, okay? But, if you want to get a first in your assignment over Christmas, you should make sure and read that chapter and figure out all the rest of the stuff with PVectors. But now you've got an introduction. Yeah?
Sorry, what chapter didn't catch that?
Daniel Shipman's book on the nature of code, right? So it's the guy that wrote the processing book that I used. He's got another book which is a free book called The Nature of Code, and he's a great chapter about PVectors. And I'll link to it from the GitHub, and I'll circulate some stuff. Okay, so that kind of wraps up our class for today. Thanks, everybody.
Thank you.
See ya.
Which one's better? Creating new variable velocity